Go.
Good morning, sir. I am Julie Franz Interno, and today we'll be talking about how to solve for the electric field. So the problem is a positive 20 nanocoulomb point charge is placed on the y-axis at y 0.05 meters, and a positive 38 nanocoulomb point charge is placed on the y-axis, wherein y is equivalent to negative 0.1 meters. And another 2-point charges, negative 16 nanocoulomb and negative 45 nanocoulomb, is placed at 35 degrees at 0.2 meters counterclockwise from the negative x-axis, and 0.4 meters at 25 degrees clockwise from the positive x-axis, respectively. So what is the direction and magnitude of the electric field at the origin? So we are actually following the Guthaccia mnemonic, wherein G stands for given, U for units, F for FPD, A for apply equation, C for components, T for total of components, R for resultant, and A for angle with reference axis. For the given, we have 4 given point charges, where in the first charge we have positive 20 nanocoulomb. For the second charge, we have 38 nanocoulomb. For the third charge, we have negative 60 nanocoulomb. And for the fourth charge, we have negative 45 nanocoulomb. For the distances, for the first distance, we have 0.05 meters. For the second one, we have 0.1 meters. For the third distance, we have 0.2 meters at 35 degrees. And for the fourth distance, we have 0.4 meters at 25 degrees. And the unit used in the problem is nanocoulomb, which will be converted into coulombs later on by multiplying the given point charges to times 10 to the power of negative 9 coulomb. Now for the FPD, let's hear Isa Santino.
So for the free body diagram, we will be looking for the electric field of the fifth point. Now, since our first point is positively charged, it will repel our fifth point. And now since our second point is positively charged as well, it will repel the fifth point, which is why it goes upwards. Now, since our third and fourth point are both negative, it will attract our point, which is why it will move towards its direction. So for our fifth point, its free body diagram will be like this. Now, after having the free body diagram, we will be applying the equation for each point.
Now in calculating for the electric field for each point, we have, for the first point, we have E1 is equivalent to, in calculating for the electric field of each point charges, we will be following this equation, wherein K is the coulomb's constant, and Q the point charge, and R as the distance between the charges. So now E1 is equal to KQ1 over R squared, where K is equivalent to 8.99 times 10 to the power of 9 newtons times meter squared per coulomb squared, times Q1, which is equivalent to positive 20 nanocoulomb. 20 times 10 to the power of negative 9 coulomb over R squared, the first distance, 0.05 meters squared. And the answer for the first point charge is 71,920 Newton per coulomb. The second point, we have K Q2 over R squared 0.99 times 10 to the power of 9 Newton times meter squared over coulomb squared times the second point, which is equivalent to 38 nanocoulomb, or times 10 to the power of negative 9 coulomb over r squared 0.1 meter squared. And the answer for the second point is 34,162 Newton per coulomb. For the third charge, we have KQ3 over R squared 8.99 times 10 to the power of 9 Newton times meter squared over coulomb squared times Q3, which is equivalent to negative 16 nanocoulomb, or times 10 to the power of negative 9 coulomb over r squared, which is 0.2 meters squared. And the answer for the third charge is 3,596 Newton per coulomb. And for the last one, which is E4 is equal to KQ4 over r squared. 8.99 times 10 to the power of 9 Newton times meter squared over coulomb squared times Q4, which is equivalent to negative 45 nanocoulomb, or times 10 to the power of negative 9 coulomb over r squared, which is 0.4 meter squared. So the answer for the fourth charge is 2,528.44 Newton per coulomb. And now for the components, let's hear Isa Centino.
So now for the components, we will be getting the x and the y component. So for Q1, Q2, Q3, and Q4. For Q1, we got 7 for Q1, it is in the y-axis. So our x-axis will be 0, and our y will be, since it is pointing at the positive x-axis, pointing at the positive y-axis, it will be positive 71,920 newtons per coulomb. And for Q2, we have it facing downwards at the negative y-axis, which is why our x will be 0 and our y will be negative 34,162 newtons per coulomb. Now, for Q3 and Q4, since these are tilted angles, we will be looking for the x and y components. So here, for the Q3x, Q3y. Our Q3 value is 3,596. And to get the x component, we'll be multiplying with cosine, and the angle is 35, so cosine 35 degrees, which will be 2,945 newtons per coulomb. And for y, we will have 3,596 sine 35 degrees, which will be 2,062 newtons per coulomb. Now, we have to get for the fourth point as well. Q for x component and Q for y component. So for Q4, we have 2,528 cosine 35 for the x, 25 because it has a 25 angle from the positive x-axis. Just cosine 25, which will be 2,291 newtons per coulomb. And for a y, we will have 2,528 multiplied by sine 25 degrees, which will be 1,068 newtons per coulomb. Now we will put this in the x and y component. Since our third point is based on the left axis, x-axis, we will have a negative. So negative 2,945 newtons per coulomb. And since this is at the negative y-axis, we will have negative 2,062 newtons per coulomb. Now for our fourth point, since it is located at the positive x-axis, we'll be having 2,291 newtons per coulomb. But it is also based at the negative y-axis, which will be negative 1,068 newtons per coulomb. And we have to add all of it or get the sum of all of it. So the sum of the electric force, electric charge of x component is negative 654 newtons per coulomb. And for the sum of the electric charge of our y components, it will be 34,628 newtons per coulomb. Now, since we are finished with the components and the total of the components, we will be getting the resultant, which will be, since we have a negative x, to be going towards the direction of the negative x-axis. And since we have a positive y charge of y, it will be going towards the positive direction of y. Now we have to get the resultant to get the magnitude of the total electric field. Okay, so the formula for the resultant is square root of the sum of the electric charge of x component squared plus the sum of the electric charge component y squared. So, since we got their values a while ago, we will be substituting it into the formula, which will be negative 654 squared plus 34,628 squared. And the total will be 34,634.18 newtons per coulomb. So that will be the magnitude of our electric field at the fifth point, or as we call it, the origin. Now, we have to get the angle with the we have to get the reference angle, and we can do that by inverse tan multiplied by y, absolute y over x. And our y value is 34,628 over 654, which will give us an angle of 89 degrees. So, the answer as said a while ago, we were looking for the direction and the magnitude of the electric field at the origin. And since we have the magnitude, the answer will be 34,364 newtons per column at 89 degrees. 89 degrees. Clock. 89 degrees. Counterclockwise. Oh wait. Clockwise. Above the negative x axis. So that will be our answer. 34,364 Newton per column at 89 degrees clockwise from the positive x axis. So that will be all. Oh my gosh, I don't even